Welcome back, everyone. It's AI with Chucky. Today we're looking into the Flux Klein 4B image Outpainting Lora workflow right inside Google Colab. We are going to use Outpainting to seamlessly expand the canvas of any images, hallucinating those missing parts and uncropping our favorite generations with mind-blowing coherence. Best of all, we aren't relying on expensive local hardware or complicated interfaces. We are deploying this entirely in the cloud using Google Colab's free T4 GPU. It's lightning fast, highly accurate, and runs completely for free. Let's jump right into the setup. To get started, head down to the description below the video and click the link to my GitHub repository. Once you arrive at the AI with Chucky Colab Notebooks page, scroll down until you locate the Flux Klein 4B Outpainting Colab. Go ahead and click the blue Open in Colab badge to instantiate the notebook. Once the notebook environment loads in your browser, the very first step before executing any Python code is to perform our first ritual. So let's ensure our cloud hardware is properly allocated. Since we are running this entirely on Google Colab's free tier, we need to explicitly claim our compute instance. Navigate up to the top right corner of the UI and click the drop-down arrow next to Connect. Select Change Runtime Type and verify that the T4 GPU is selected. Once confirmed, click Save and we're good to go. Alright, let's move down to the first cell. Step 1 to initialize core and custom nodes. Go ahead and execute this cell by clicking the play button. If you receive a standard warning stating this notebook was not authored by Google, simply click Run anyway to bypass it. We are now ready to initialize the backend. When we run this initialization cell, the script pulls in the necessary core repositories and PyTorch dependencies configured for CUDA 12.1. If you monitor the standard output in the console, you'll see it fetching required custom nodes to properly route our parameters from the Colab sliders directly into the engine. This initialization takes a minute or two as it builds the environment and resolves dependencies. You'll know the container is successfully configured when you see the green checkmark appear next to the execution button and the environment ready string prints at the bottom of the log. Moving along, let's scroll down to Step 2, the high-speed asset downloader. Go ahead and run this cell. To execute this specific outpainting pipeline, we need to populate our models directory with the correct weights. First, we are pulling the primary onet, Flux.2 Klein 4B. Alongside the onet, the script grabs the Qwen 3.4b text encoder and the standard Flux VAE. However, the crucial component of this setup is the FAL Flux.2 Klein 4B Outpaint Lora. Unlike a standard character or style Lora, this file specifically understands edge continuation, context blending, and spatial hallucination. It forces the Flux onet to evaluate the unmasked region of your input image and seamlessly denoise the extended canvas to fill in those missing cropped-out areas without degrading the original image. Once the console outputs all assets secured with precise field names, our model directories are primed. Now let's proceed to Step 3, the dynamic single outpainting execution. This is where we initiate inference on our free T4 GPU and expand our images or outpaint. Before executing the cell, let's review our parameters. First, we have the max base dimension slider, currently set to 1024. You can increase or reduce it to determine the size of your result. Next, we have steps. Because the Klein 4B architecture utilizes a turbo distillation method, we only require 4 sampling steps to reach a high-fidelity converged image. The seed is set to 0 for random noise. Below that, we have our padding parameters. This defines exactly how much of space we are appending to the original image to later uncrop or fill it. You can see we have sliders for pad, left, right, top, and bottom. For this test, I want to evaluate the model's ability to extrapolate horizontal environmental data. I'm going to go with the default adjustments of the pad left slider at 300 pixels, which mirror the pad right slider to 300 pixels as well. I'll leave top and bottom padding at 0 because I don't intend to outpaint vertically. With the parameters locked, click the Run button. The Python script will execute and invoke an upload widget where you'll need to input your raw image. Click Choose Files to open your local directory. I'm going to navigate to my folder and select this image of a woman riding a scaled frog, dragon-like creature through a swamp environment. Upon upload, watch the console logs. Because this is the initial generation for this session, the backend server must load the weights into the T4's VRAM. This cold boot phase takes roughly 2 minutes, but this will drop down in our next generation to a minute or less since the model weights would have been loaded. The script then executes the inference, generation, and prints complete. The inference is finished, and the script automatically triggers a local download of the output image so you can save it on your device and still displays it for your viewing. Let's compare the input image and output and analyze the spatial coherence. The structural continuity here is exceptional. In the original input image, the composition was tightly cropped, completely truncating the sides of the creature's face and the rider's arms. The Flux Klein model processed the existing edge pixels and flawlessly hallucinated 300 pixels of new visual data on both the left and right axes. Look closely at the complex texturing of the dragon's scales on its back and the anatomical structure of the wings on the right side. The model did not resort to simple blurring or repetition. It extrapolated anatomically correct features that maintain perfect logical consistency. Furthermore, the atmospheric swamp background perfectly matches the depth of field, the bokeh characteristics, and the color grading of the base generation. Crucially, there are no visible seams or degradation where the original image ends and the new generation begins. If I open the original image and place it side by side with our outpainted output, the capability of this pipeline is undeniable. We've taken a constrained, cropped image and successfully expanded it with flawless context retention in just 4 sampling steps. We can try a second image. This is an extremely cropped photo of a woman and parts of the shoulders have been cropped. This time, let's use custom parameters for the padding and then run the cell. Then upload the file and wait for the generation. Now the result is ready, and you can see how well the model fill in parts of the image to reveal more details. We can do more to expand more sections of the image, but let's leave it as that and move on to the final cell. Now, scroll down to the final cell in the notebook. This module functions similarly to step 3, but it's configured to iterate over an entire array of uploaded files sequentially. In essence, this allows you to outpaint several images at a go. So, you can adjust for uniform padding parameters to test a different extrapolation scenario. Execute the cell to trigger the upload widget, and click Choose Files. You can highlight multiple files from your local drive. Select both and click Open. Once the transfer is complete, the cell begins processing the queue immediately. The significant advantage here is that the model weights are already cached in the GPU's memory from our previous single image execution. We bypass the cold boot loading phase entirely, allowing the turbo model to execute the batch inferences back-to-back with minimal latency. If you monitor the standard output, you'll see the script logging processing image 1 of 2, saving the output, and then it instantly transitioned to processing image 2 of 2. It takes around 40 seconds to process a single images, which means you'll need around 4 minutes to outpaint 10 images. With this same duration it took me to outpaint 9 images earlier before this video. Once the entire queue has been processed, the Python wrapper automatically compiles the files, compresses them into a single zip file, and triggers a download request. You'll see batch outpaint results zip pops up in your downloads. You just have to save. I'll extract the zip to my desktop. Let's analyze the portrait of the smiling woman first. In the base image, the crop severed the top of her hair and completely eliminated her left shoulder on the right side of the frame. The Flux pipeline perfectly reconstructed the top of her head, maintaining the intricate structure of the metallic tiara. It matched the global illumination and complex hair texture perfectly. On the right side, the model accurately extended the velvet fabric of her dress. Moving to our Dragon Rider image, the model successfully hallucinated a coherent, overcast sky above the rider, improving the spatial framing. This batch execution block is a highly efficient tool. You can queue up dozens of cropped images, lock in your padding dimensions, and let the cloud GPU handle the compute, leaving you with a neatly packaged archive of extended images, generated rapidly and entirely for free. And, because we are operating on Colab's free tier, our storage is entirely ephemeral. Keep in mind that when your runtime is disconnected, Google will wipe this temporary storage. Always ensure your batch zip files are fully downloaded to your local machine before closing your browser instance. When you have completed your workflows, click the drop-down arrow next to the RAM and disk metrics in the top right, and select Disconnect and Delete Runtime to release the T4 GPU back to the allocation pool. And that wraps up today's tutorial. If you found this video useful, please drop a like, hit subscribe, and enable notifications so you don't miss future open-source tool breakdowns that runs on free hardware cloud instance like Google Colab. Please do care to support the channel on Patreon because it takes hard work to build Colab notebooks, and your support get these workflows coming. The link is in the description. Also, I've dropped a link to my GitHub repo for the notebook in the description below. If you encounter any exceptions while running the notebook, or if you want to suggest a specific model pipeline for a future video, leave a comment below. I review all of them. Thank you all for watching. Keep pushing the boundaries of these models, and I will see you in the next one. Peace.